Hi, we're going to go through the answers to 27.2 now, okay, about binding energy. Some really important information you're given at the start is that the mass of a proton, this will be the rest mass, is 1.00728 U. The mass of a neutron is 1.00867 U. And randomly on this page, they say that 1 U is equal to 931.5 megaelectron volts, but I think that's what it was in the old specification and it's just a typo, so we're going to go with 931.3, which is what it is in your specification. And we're going to have a go at the questions. So question 1 asks, explain what's meant by the binding energy of the nucleus. So you should be talking about the fact that binding energy is the amount of energy required to separate a nucleus into its constituent nucleons. And then it says sketch a curve to show how the binding energy per nucleon varies with mass number as shown approximate scale. So you want to sketch this sort of like this, and then on the bottom you'll have mass number, and then on the side you'll have binding energy per nucleon. So I just use A for nucleon because it's the mass number. And then the maximum here is between 9 and 8 is just below, and then the mass number here would be 56 for iron. Okay, so that's the sort of scale that you want. Question 2. Calculate the binding energy per nucleon of 12,6 carbon. Okay, and it gives you that the mass of the carbon is 12 U. The reason it's spot on is because the mass of carbon is used to define U, so that's why it is dead on 12, okay, and then all the others come from that. So what we're going to do to start with is we're going to find out the mass difference. So you've got 6 protons using this number up here, and then you'll have 6 neutrons as well, and you're going to minus 12 from that. So you should get a change in mass of 0.0975 U. Then we're going to calculate the binding energy, total binding energy. So we're going to calculate that mass difference by 931.3, which gives you a binding energy of 89.12541. We then want the binding energy per nucleon, so divide 89.12541 by the number of nucleons, which is 12, and you get an answer of 7.43 megaelectron volts. Okay, so that's your answer to question 2A. Question 2B wants you to find the binding energy of iron, which is the one with the most binding energy per nucleon. So you find the change in mass first. Okay, so you're going to do, remember the change in mass equation, or the mass difference, is ZMN plus A minus Z. Sorry, ZMP, A minus Z, MN minus M of the nucleus. So we've got 26 protons, so times that by the mass of the proton, plus 56 minus 26 neutrons, so 56 minus 26. And then you're going to take away the mass of the nucleus, and it tells you that the mass of the nucleus of iron is 5.92067. Gives us a mass difference of 0.5287 U. Binding energy 0.5287 times 931.3 gives you the binding energy of 492.387623. So then the binding energy per nucleon is 492.387623, all over the number of nucleons, which is 56, and you get an answer of about 8.8 mega electron volts. So this here on your graph would be 8.8. Okay. Question 3. Question 3 says calculate part 1, the binding energy of a alpha particle, and it says the mass of alpha is 4.00125150 U. So to find the binding energy, you need to do the change in mass. You've got 2 protons. And you've got 2 neutrons, because 4 minus 2 is 2. And you're going to take away the mass of the nucleus, which gives you a change in mass of 0.0304 U. Going to find the binding energy now, so you're going to take that mass difference, times it by 931.3, and you get an answer of 28.31152 mega electron volts. Then want to find the binding energy per nucleon, so you're going to take that number and divide it by the number of nucleons, which is 4. So you get about 7.08 mega electron volts. Next part wants you to figure out the binding energy per nucleon of a 3,2 helium nucleus. So that's an isotope of helium. This isotope's made in the sun during fusion. So it tells you that the mass of this helium is equal to 3.01493 U. So the change in mass is going to be the number of protons, which is 2, times 1.00728, plus the number of neutrons, which is 1. So you're just going to add on 1 neutron. You're going to take away the mass of the nucleus itself, which gives you a change in mass of 8.3 times 10 to the minus 3 U. So therefore the binding energy will be 8.3 times 10 to the minus 3 U times 931.3, which gives you a binding energy of 7.72979. So then the binding energy per nucleon, you need to divide that number by how many nucleons there are, which is 3, and you get 2.58 mega electron volts. And this goes to show really clearly, obviously this helium, so alpha is the same as helium-42, normal helium in the periodic table. So by becoming bigger, it's on the left hand side of this graph here. So by becoming bigger, from here to here, you increase the binding energy per nucleon actually quite significantly, and so it becomes more stable. So this is more stable than this, okay, in terms of nuclear stability, not in terms of the fact it's got a charge, so it's radioactive. If it was an alpha, it would have a charge that's radioactive, and that can then disrupt, obviously, living systems. In terms of nuclear stability, this is more stable. Also, we know this would be stable because it's got the same number of protons and neutrons, and so things with the same number of protons and neutrons, if you think back to that graph we drew during decay modes, they're on the stability line. so they're stable. Right, question 4 gives you part of a different part actually of the process of nuclear fusion in a star. And it says complete the equation to show the fusion reaction that occurs when two protons fuse together. So I added the values here. This is +1, isn't it? Yeah, beta plus. And also because the lepton number on here is 1 and this is an anti-particle, you need an anti-lepton, you need a neutrino here, an electron neutrino, to make sure that these two lepton numbers cancel each other out. And then for part B, it asks you to calculate the binding energy per nucleon of the 2, 1 nucleus. So you're going to do, you've got 1 proton and 1 neutron, so the change in mass is going to be 1.00728 plus the neutron, and it tells you the mass of this hydrogen is 2.01355. You're going to take that away. So you get a change in mass of 2.4 times 10 to the minus 3U. So the binding energy, 2.4 times 10 to the minus 3 times 931.3 is 2.23512 mega electron volts, but you want the binding energy per nucleon, so you're going to divide that by 2, top number's 2, and you get 1.12 mega electron volts, so not very stable. So in fact, because this is not very stable, it actually fuses, it then fuses to make this, and then some of these fuse to make this. So this actual process of these 3 elements, let's change that to helium, that is what happens in a star. So you're going from here to here to here to here, and every time you're increasing the binding energy per nucleon. Right, I hope that was helpful. Let me know if you have any problems.